Hello everyone. My name is Saulius Gudzius and I will be the chairman of this section of electrical engineering. Of course, it's a little bit strange to discuss in conference using this remote assistant devices, yes, and usually conference is communications between the researchers in life, but now we have situation in which we should proceed in such a way. So everyone know what is electricity, and everyone in this club know about the importance of the electrical engineering, yes? So we are just three, as I understand, yes, three presenters and I, yes, so four persons who should discuss about electrical engineering, yes. So, and we have very interesting, of course, presentations, and they come from different countries and from different institutions with different experience, yes. So maybe we should start our session, yes. And I would like to ask Renata Markowska from Białystok Technical University to start our discussions about the electrical engineering. Please. You are first.
Good afternoon. I'm from Białystok University of Technology, Poland, and my work was started on a request of an expertise on the susceptibility of the intrusion detection systems to electromagnetic disturbances caused by lightning discharge. The electronic systems containing extensive cable installations located outside building structures are particularly endangered to damage or interference in operation during lightning discharge. Ensuring proper protection of such systems requires detailed knowledge of the threat levels and accurate tools to assess these threats. For this purpose, various theoretical methods are used, ranging from simple analytical solutions to very complicated advanced numerical methods based on the electromagnetic field theory or hybrid approaches. The problems are being studied widely for electrical power lines and for telecommunication systems. However, there is no sufficient knowledge of the lightning threat in other dedicated systems. The object of my work is an underground electronic cable intrusion detection system based on buried cable sensors made of special coaxial cables. A single sensor is composed of two parallel cables, a transmitter and a receiver. A special construction of the outer conductors of the cables allow to effectively radiate and receive the operating signal. The sensory cables are connected to an electronic device, an electronic controller, and the other ends of the cables are terminated with passive devices. The controller can support two cable sensors. Hence, the detection area is up to 800 meters of length or perimeter. The area may be increased further by creating a network composed of many controllers, many base units, in which they may be arranged in a form of an open line or of a closed loop. The network systems, irrespective if open or closed, can work either with or without the galvanic continuity between the adjacent units. These two configurations may vary in the susceptibility to the lightning electromagnetic pulse. In the connected configuration, high surge currents may be observed in the loops formed by the outer conductors of the sensory cables and ground, which may lead to thermal or electromechanical effects on the cables. These currents will also induce the surge voltages between the inner and outer conductors of the sensory cables. In the isolated configuration, the high surge voltages between the cables and terminators of the adjacent units may arise. If the isolated cables are located close to one another, the surge voltage stress may lead to the electrical breakdown of the insulation and the uncontrolled flow of surge currents. Comparing these two configurations with respect to the threat levels may be helpful in choosing the optimal protection measures with the optimal configuration. The problem is complex due to strong effects of at least two electromagnetic couplings. The conduction of current in ground, causing the transient uneven ground potential distribution, and the magnetic field induction. These phenomena are significantly dependent on many factors, mainly the point of the lightning strike, the distance, of course, the lightning current parameters, the configuration of the system, and the soil parameters. Solution to the problem required advanced numerical methods. In the applied method, the computations are performed in the frequency domain for harmonic current source. The transformations between the time and the frequency domains are done using the fast Fourier transform. The system is represented by the three-dimensional structure composed of thin cylindrical conductors divided in short segments located in multi-layered medium. The two potential electric field integral equations formulated based on Maxwell's equations are solved numerically with the method of moments. The system under study is composed of two controllers, each supporting two cable sensors. Along the transition detection zone, a lighting system is usually installed. It was assumed that the lightning strikes the lighting pole nearest to the controller C1. The lightning current is represented by the standard recommended waveform with 100 kiloamperes peak value, and this current flows into the horizontal grounding electrode of the lighting system. For the configuration with metallic continuity, the following quantities have been computed. The lightning current distribution in the grounding electrodes, horizontal and vertical, the transient potential differences between the devices, and the surge currents in the outer conductors of the sensory cables. A very similar situation will occur in the isolated configuration, but in this case, also the surge voltages between the isolated sensory cables at the places of their approach were calculated additionally. The surge currents flowing into the vertical grounding electrodes of the controllers differ visibly for both configurations. In the case of the isolated configuration, only the short time component of oscillatory type is present, whereas for the connected configuration, there is also the long duration component, which resembles the waveform of the lightning current. The surge currents in the outer conductors of the sensory cables are very similar to the currents flowing into the vertical grounding electrodes, but they have much stronger, much higher the oscillatory type components. To assess the threats of thermal or electromechanical effects of the surge currents on the cables, the current of the highest peak value, the longest duration, was taken into account, which is in the case of the connected configuration. But even in this case, the estimated values of the temperature rise and the electrodynamic force are low enough that they will not cause damage to the cables. For both configurations, the potential differences between the controller located nearest to the point of the lightning strike and terminators are very similar and close to the potential of this controller with respect to the remote ground. However, the potential differences between the controller located farther from the point of lightning strike and terminators are significantly dependent on the configurations, and this concerns both the peak value and the waveform. For the isolated configuration, the surge voltages between the sensory cables and terminators at the places of their approach do not exceed the half value of the potential of the controller located nearest to the point of the lightning strike. Taking the electrical withstand of the typical polyethylene insulation of the sensory cable, this potential difference of 40 to 80 kilovolts shall not cause the insulation breakdown. Finally, the peak value of the surge voltage between the inner and outer conductors of the sensory cables was estimated approximately based on the peak value of the surge current flowing in the cable's outer conductor, the transfer impedance between the outer and inner conductor, and the cable length. Then the value of voltage was compared to the level of immunity to surge voltage of signal interfaces of the electronic devices. It was shown that in the case of the connected configuration, the resultant peak value of the surge voltage of 3.4 kilovolt is likely to exceed the withstand level of the controller's interface. In the case of the isolated configuration, the resultant peak value of voltage, 1.4 kilovolt, may be regarded as below the withstand level of the controller's interface. To conclude, the object of the work is the underground intrusion detection system based on buried cable sensors. The problem, whether the adjacent units of the system should or should not be connected together in order the system is less susceptible to the lightning discharge, was analyzed. The problem is complex since the behavior of the system depends on many factors. It was shown that there is no threat related to thermal or electromechanical damage, as well as there is no threat related to the electrical breakdown of the insulation of the sensory cables. However, there is a serious threat of the breakdown of the controller's interface, especially for the connected configuration. Finally, it should be pointed that different threat levels for different higher soil resistivity or different steepness of the lightning current might occur. This is the subject of the further research. Thank you for your attention.
Microphone. Yes. Thank you, Renata, for your presentation. I tried to unmute myself, but someone else tried also to unmute, so short break. Okay, so it's quite interesting. When you're talking about lightning, it's very popular nowadays in Lithuania. We have a lot of lightning as well as in Poland, I see, yes. And it's caused a lot of problems, but the discussions maybe help us to solve some problems, yes? Maybe someone has questions about presentation? Questions for Renata, from audience, for 3 or 4 guys audience? Okay, so I have a question. Maybe it can be found some solution to avoid this high level of voltages in such situation. What do you think? Yeah.
Okay. Yes, typically over voltage protection devices should be installed in the case of the controller's interfaces.
Yeah.
And that should be in this case, for this particular case. But as I told, some other effects may be more visible when you start considering different parameters of soil, for example, or different parameters of the waveform of the lightning current. That's because of the different potential distribution in ground, and that may be not entirely. Maybe the surge protective devices would be not the only device to apply in this case. Maybe some other aspects of equipotential bonding should be analyzed also.
But maybe it's possible to connect all these 2 parts because usually when you would like to avoid such kind of the over voltages between 2 different systems, maybe it's possible to connect them by using some special devices, maybe some dischargers or something like this, to equalize the equipotential space and to get the same voltage in all parts of the devices, and in such case avoid the breakdown of this gap.
Yes, in one of the configurations which was analyzed, the system was connected directly.
Yeah.
But as you see, the direct connection is less, is worse than the isolated one, provided that the isolation is withstand the level of threat. Yes, so isolated would be better,
much more better. Yes, and the length of the cable change the situation or not? If you
yes, it will. Yes, it will change the situation, of course.
Yeah, so you can make a longer cable in such cases.
Yes. This was analyzed for the highest length of the highest possible length, because it's up to 800 meters, can be operated by single controller.
And you have incidents with this kind of controllers in your experience? Or
yes, some company asked me for an expertise in this system, because they had some problems with such systems, and they wanted to know different scenarios would be better to connect or not to connect, because direct connection of these two systems is better for them, because they may be the power supply voltage can be done by through the sensory cables, and each controller does not have to be supplied by separate power lines. So direct connection is better from this point of view, but as from the lightning point of view, it could be the worst.
Okay, so thank you, Renata, for your presentation.
Thank you very much.
So it's nice to see you again. Okay, so thank you.
Thank you.
And now we have second presenter from Department of Mechatronics and Electronics, University of Žilina. And the title of the presentation is Electro-Thermal Modeling and Experimental Verification of Power Semiconductor Diode.
Okay, so my name is...
Welcome to the conference and welcome.
Thank you.
So please present your topic.
There's a question, can you hear me?
Yes, we hear you very well.
Okay, so I also started to share my presentation.
Yes.
So thank you very much for the introduction. And I will briefly discuss the proposed paper, which is focused on the electro-thermal modeling. And the paper was also undertaken in the cooperation with the industrial partner, which is a Bosch Drives and Pumps. So what was the main motivation for, just a second, for this research was to design a very precise simulation model of the power semiconductor diode, while the use of this simulation model will consequently be for the estimation of the lifetime parameters under various operational scenarios of this power diode. So the main contribution is that we have found how to model multi-domain power device, and on which we can apply some methodology for the lifetime estimation, because we know that the thermal or the temperature and thermal performance is the main issue which is influencing the life behavior of electric components. So there is some parts related to the geometry modifications and the investigation of the internal internal composition of the power switch or power diode. Then we have described the multiphysics interconnection for the finite element method analysis. So we have been describing electrical and thermal domains. Then what was very important was to identify the variables which are responsible for influence on the thermal performance. And at the end of the paper, we have provided verifications. So we have realized experimental measurements in a laboratory, and we have compared the results from simulation with these experiments. We have found some relative error. We have evaluated it, and now we are still optimizing these models to be more precise. So on this slide, we can see the package or the geometrical properties of the power diode. So it is composed of the package, which is located at the upper part of the slide. And it is composed of the PN junction, which is located inside of this package. The data of the semiconductor diode have been received from manufacturer, so we know the exact parameters of the chip, of the silicon chip. Here you can see that we have specified some parameters, geometrical parameters. So if you define in this way the model in a console, because the console was used as the software, then you can use this model for wide range of portfolio, so you can easily modify the geometric properties. So this was the purpose, also to have some universal simulation model. On this slide, you can see the boundary settings for both electrical currents and also for the heat transfer in solids. So each main domain, like die, package, contacts, pads, and the environment, have specific definitions regarding the boundary settings and also material parameters. So you can see on the right side that we have been defining also material parameters related to the manufacturer's data. The physics which was used is considering the calculation of the power losses, which are generated based on the current flow. So in this way, we are connecting the electrical and thermal domains. So the thermal performance is calculated from the electrical conditions within a specific circuit. The specific circuit is a power converter, and it will be discussed later. Okay. Regarding the modeling, there is no other issues which are important. So we have developed a simple test stand in a laboratory. So you can see on the picture that there is a simple boost converter where the diode is used, and the input-output parameters, electrical parameters, are listed in table. I'm sorry, there is a mistake. It is not material parameters, but the electrical parameters of the power converter. So it is boost converter. It's boosting from 12 volts to 24. And the variable was the input and output converter current, so the output power. The diode has a nominal current of 500 milliamps, and we have provide the measurements under 50% of its nominal loading. It was due to fact that we did not utilize any heatsink or forced cooling, because in order to validate the model, you cannot use the cooling system, because then we cannot be sure about the accuracy of the model. Okay, the switching frequency was 100 kilohertz, what is a nominal parameter also for the diode, and the ambient temperature was 25 Celsius. Okay, so after this, you can see that we also have been using the Zimmer, which is a spectral analyzer just for the measurement of the efficiency of the converter, but it does not have the direct impact because the thermal performance was measured by a thermovision camera. The Zimmer was used mostly for the identification of the voltage and current ripple at the input and output. Here is a slide related to the electrical modeling of the volt amp characteristic. So we have used indirect methodology to define the conductivity, electrical conductivity, because the manufacturer are defining this value just for a specific forward current. So you can see that what we found was to simulate the volt amp characteristic in console. So this picture, which is a C, which is marked as a C, is a modeling of the volt amp characteristic in console, and this is very important if you are changing the load of the diode, and because you can see that there is a dependency of the voltage and current, what is principal dependency. So in this way, and it is more in detail described in paper, we have found the volt amp characteristic for electrical domain or electric domain in console. And now here we can see the thermal measurements. So for 3 various average currents, we have provided these measurements. So the voltage was coming from 118 degrees up to 150, and for the measurement where is 500 milliamps, this measurement was the last one, because after this measurement the diode was destroyed due to very high temperature on the silicon. You can identify the hotspot inside of the diode, so there is a silicon chip which is being heated. And also what we have tried to compensate was the effect of the cables. You can see that the cable is acting as a small cooler. So now we have a new let's say converter where the heat is distributed on the PCB pads, and the effect is also added within the simulation model. So the study is now extended. Okay, similar to experimental measurements, we have provided the simulation measurements. So these are the 3 states. The legend is inversed, opposed to previous situation, but the important is the results, which is summarized here. And this is the comparison between measurement and simulation, and also the evaluation of the relative error. So here we can see that if we are going to the value of the forward current around 0.3 amps, we are reaching -2 or -1% of the relative error. The error is higher for the higher forward currents and also the higher temperatures. And this issue is being under consideration now, as I mentioned, to have a better test stand or test converter, and also to include the effect of the pads of PCB within the model. At the end, this result is acceptable for the evaluations of the lifetime, but needs to be, of course, improved to have better results for the future applications and to extend its use. So thank you very much for your attention.
Thank you for a nice presentation and interesting presentation. So, audience, please ask questions. Because I am a little bit from different side or different part of electrical engineering. Yes, I am a power engineer. So for me, is volts and millivolt amperes. It's not so big values, and a little bit strange how these values make so big damages. But this situation is similar in high voltage equipment, where we also trying in high voltage laboratories to destroy something. And my question is, for what purpose you do such experiment? We know that in high voltage we do this for the testing of the isolation, yes? Testing the lifetime of the isolation and testing of the range, in which extent we can increase voltage and insulation will still be able to resist such high voltage. But in your case, what is a practical application of your experiment?
Okay, thank you very much for the question. I fully understand what is behind. So the main use of this model or main purpose is to have a very precise simulation model which is considering electro-thermal behavior. With this model, because it was a research task for the industrial partner, and they would like to find in which operational scenario or operational case the diode is expected to be damaged. So you can specify the electrical parameters, and you see the thermal behavior, and you see how to protect the device in order to prevent some damage.
Okay, so it's for protection, yes?
Protection and estimation of possible lifetime.
Yeah. And what kind of protection you usually use for this, for protection of such kind of devices?
So for these power electronic systems and converters, I think that the best protection is to have a very precise design of the final prototype. So it is a task related to the PCB optimizations, cooling optimizations, and so on.
So differently from, it's a little bit different from power engineering, yes, where you can predict the future. In power engineering, we can't predict the future because it's not possible to predict the lightning stroke amplitude and so on and so on. So we should be ready for outrage of voltage, of current, and so on and so on. So your solution is to make the design of the equipment as optimal as possible, yes?
Exactly.
Yeah. Okay, so it's a difference between us, yes?
But maybe this is life.
This is life, yes. Okay, so maybe more questions? And what about other voltages? I just wondering, if you have some electronic device, you can construct a very optimal device, but of course, other voltages can occur.
Yes, but this is a issue for which the other I don't know, active clamping can be used within the converter topology or other stuff for the sensing and monitoring. But mostly these power devices, which are critical, are protected with the use of clamping circuits, so some RCD snubbers and so.
But but it is possible to work in such outrage, such outrage characteristic of your diode. It's possible. You decide how long it takes to destroy this diode.
Yes, it depends on how long. Yes, this fault is applied, but it cannot occur. It must be as safe as possible. And this is a DC-DC converter, so there is a little bit different point of thinking, because we have a low voltage levels, and mostly these levels are stable, because the converter is supplied from some battery system, for example, so you cannot predict any fluctuations on something like that.
So it's totally insulated system, yes?
Yes.
Okay, it's not for the PV.
No,
it's just for some very safe systems. Yes. Okay. So thank you for your presentation. Thank you for interesting ideas, and I hope for the attendance it was interesting to hear about your investigation. Okay, and good luck. Thank you.
Thank you also. Bye.
Thank you.
Bye. Okay, it's a little bit strange when you working in this Zoom environment, and it's not so. It's better to work in live meeting than in this internet. Okay, so who is next? Next is presenters from China, as I understand, but there's no presenters from China regarding the design of high power energy storage bidirectional power conversion system. It's no presenters from this company, yes. So next it's my turn, and because my PhD student has some urgent duties, so I will present some this topic, and I should share my presentation for you. Okay. So you see my presentation on your screen, yes? I just checking, yes? Yes, okay. So as you understand probably, I'm not from low voltage, but I'm from high voltage engineering, from power engineering. And I'm working in the department of electric power engineering, and we're dealing with high voltage, high current, power, and of course with energy systems. So it's usually when you're talking about research, about investigation in energy system, you usually talk about the consumers. Because it's consumers, it's the main persons who is most important element in power system. Without consumers, without you, with your power electronic devices, with your needs for high quality energy, it's will be no need for the energy system. Yeah. So you exist, and we exist for you, for your needs, and try to make the energy quality as high as possible, and of course make the reliability of power system as high as possible. Of course it costs money, and who pays this money? Of course you. It's consumers' duty to pay money for the reliability and for the quality of the energy. So of course we should make find the ways how to increase such the reliability of the power system, find the way how to do this in cheapest way, and in cheapest and in fastest way. So a few years ago, maybe 2 or 3 years ago, our transmission system operator, its company which care about the high voltage network, asked us to try to make system which allows them faster and more precisely to detect and to predict the possible faults in power systems and power lines. Because you know that now, if in the past the system was centrally planned system, and the centralized planning allowed to predict how to power flows and how to behavior of the power system will change in the near future. Nowadays, everything is in the market, on the market rules, so it's not possible to predict which line will be overloaded, which line will be very important in the next hour. So it depends on the market, it depends on the consumers, and of course all lines are very important, and to switch line off it causes a lot of damage for the power system, of course, but it causes a big loss of money. So they ask us to think maybe it's possible to build some kind new, some kind interesting for them, and we try to work. And the object of the work is to analyze the possibility of determining the causes of the fault. And of course, one element of the technical of term of reference was the detect the corona discharge in the power line. So why it's necessary to do? It's two reasons. One reason that corona is the source of the losses in the power line, and another reason is that the corona is how to say, is a identificator that something is wrong in the power line, and we have some damages of the insulators or damages of the other element of the power line, and we should inspect this line and to if you want to avoid some big damages or losses of power line and losses of the money. Yes, so the task of this work was this work of the corona detection was just a part of the total work, but the task of this small part of the work was to prepare a mathematical model of the corona discharge, apply methodology based on the method of regression formulas, because we have long time experience in this field, and we have some mathematical algorithms which are very fast, and it's possible in real time to calculate the distribution of the corona discharge in power lines. So identify the corona discharge intensification using fault detection device. And it was at the first stage, we wonder that it's possible to make that the fault detection devices will be able to register the corona and detect the level of the corona and then decide it's something wrong in power line or not. And of course, according to the record of the fault, the voltage and current identifies the cause of the corona discharge increases in power line and to detect the faulted places in power line. You should understand that the length of the power lines, of the high voltage power lines, is not 1 kilometer, it's usually 10 or up to 100 kilometers. So to find the faulted place in such line is quite difficult, and of course it's costly. So if we have some devices which allow us to detect the distance where from the substation where the protection, where the damage exists, so it's possible to go to send the workers and to correct this situation and avoid the big damages. corona is the naturally existing power line, and it exists all the time. If we increase the voltage higher than its critical corona voltage, yes. You can hear corona during rain if you are not so far from the power line, or during icing when power lines are iced and you can see some noise not so far from power line, and this means that corona exists in this power line, and it's natural situation. But sometimes corona exists in power line when power line is damaged, and of course in this situation we should take some actions and to try to correct the situation. So in the calculations of the low voltage transients in high voltage transmission line, we usually use the distributed parameters of power line. If in electronic devices you use capacities, inductances, and so on and so on, so in calculations of electric power lines, you usually use some distributed parameters, which means that it's not just capacity, but it's capacity distributed through all the line. So it's a little bit different understanding, but it's come from the Maxwell equations, from the modeling of wave equations, and it's if you would like to model precisely power line, so you should use distributed parameters. And of course, the range in which, of course, we're using the signals or measurements for the detection of the corona, and the range and the frequencies of the corona discharge is from 200 to 300 kilohertz. So you should understand how it's complicated to model power line, where not just the main power frequencies exist. It's 50 hertz, as you know, you use it's 50 hertz or in Europe, or 60 hertz in other countries, yes. But if you would like to analyze processes in power system, you should be able or must be able to register the signals in very different ranges, from 50 hertz up to 1 megahertz if you're talking about lightning discharge, yes. So there is a lot of different technologies to predict faults, to find faults, to indicate that something is wrong in the power line. But according to our experience, there is no way how to use all these technologies without knowing the real processes in the power system. And of course, we mount some devices, some registrators in power system, and we mount it in high voltage substation, and it's located in corners, and we try to measure different signals in different ranges, and then try to, in this case, we try to extract the signal which comes from the corona discharge. So how it's look typical? It's maybe for someone new, it's familiar with such curves, but for who is not familiar, for people who are not familiar with such curve, it's a typical curve of lightning discharge and power line. It's a very nice curve for electricians, of course, and you can see how lightning strike indicate itself in the measurements of voltage, and its curves is symmetrical, and you can decide that it's lightning because all the phases go to the same direction, so electricians know that it's a three-phase fault, yes, in the power, it's lightning discharge in the power line. So what is our approach? Not to use some very complicated and very sophisticated technologies to identify to decide what's happening in power line, because in according to our experience, to find the common rules or to find the spectrum or find the make some mathematical manipulation, it's quite difficult, because when you measuring, as I told, when you're measuring signals in power lines, and when you're measuring the signal which comes from the different events in the power lines, the frequency range is quite big, and it can be from 50 Hz up to 1 megahertz or more. So if you try to filter something, you will lost information and you can't decide what happened in power line. So we decided to build some mathematical algorithm which allow us to decide according some future of the signal and according to the sequences of the event. And according to these different sequences of the event, we can decide what really happening in the power line and what occur in the power line and what the cause of this situation is in the power line. So if you measuring normally in power line, you have the very fine curves of voltage, and of course the current is not so fine, but curve of the voltage is very nice, and usually it's sinusoidal and symmetrical and so on and so on. So especially in the transmission system. But if something occur, you can decide if something occur, you can decide according to the changes in the curve, and you can see that the high voltage signal appear in the registrations, and according to this you can decide that something is wrong in the power line. So the reason of this signal changes can be the damage of the isolation and so on and so on. So according to our idea is that if something occur, so it should be initiate the corona discharge and and this can be registered using some fast registrators, yes. And we try to do, and we leave our registrators for more than 3 months in the substation, and we registered a lot of different events, different situations. But the problem is that the noise would exist in power line. It's very, very high. And if you filter, we try to filter the range, which is typical for the corona discharge, and try to extract this signal from the measurements, but we are not succeed. And the reason is that up to date, it's not exist some precise measurement devices which can be used in the high voltage power lines, where you know this voltage is 110 or 330 kV or more. And measurements, when you measure using some measurement transformers or other devices, they are not so precise, and it's not possible to measure corona discharge voltage, and it's not possible to decide if it's corona occur or not occur in situation when you know that something happening in power line, and you register it, you see that other voltages exist or fault exists, and you know that corona should exist also in the same time with this measurement. So we decided that it's not possible to develop such kind of devices, and we find a very simple way how to calculate the corona level in the power line. And we decided to use mathematical model. And of course, in our topic, this model is described very precisely, but of course, it's not necessarily interesting to listen about this model during presentation. And I just briefly discuss the idea of our experiment and our proposal for the transmission system operator. And our idea is to use the measurements of 50 Hertz voltage and in the beginning and at the end of the power line, and to use some electronic devices because it's a fast communication channel, what is possible to do in transmission system. It's not a big problem. And according to the measurement of main frequency voltage, and by using our model, it's possible to evaluate the level of the corona discharge in the power line, and to not so maybe precisely, but with the error which is acceptable for the technical evaluation of power line, it's possible to decide the problems would exist in transmission system power line. Of course, you should know the ambient temperature, the pressure, which is a part of the model, but using our proposed model, we can calculate the distribution of the corona in the power line and evaluate the situation in the power line and make decision if it's necessary to make some additional measurement on inspection on the power line and to avoid the fault in it, and of course avoid losses in power system. So it's briefly about our research, about our investigation, and if you have some questions, so please ask me. If everything is clear or everything is unclear. So, Renata, maybe you have questions? About corona discharge.
I have one question.
Okay, welcome.
What do you recommend for, let's say, for small houses, how to avoid corona discharge?
You see, corona is how to say, it can occur just in very high voltage systems, yes. And of course, when you're talking about private houses, so you should use devices which allow to, for example, some metal sheets, yes, which allow to protect your electronic device.
So let's say effect of corona discharge could appear, or effect, as lateral effect could appear to individual houses, yes? If something is wrong in a system.
Your house is located not so far from the power line, so this effect can occur, and you can not be able to use your electronic devices in proper way, because corona is a high frequency discharge, and of course it generates high frequency signals. So you should use shields, yes, to protect your electronic device and let them operate in proper way. So,
what about reliability of protection ways? Are they reliable, or can we trust on it, or just spend money and that's it?
Renata knows about it. It's about shielding and bounding. Renata knows they do a lot about investigation about it. So all this high frequency signals, of course, reliability, it's we have experience in building protection shield for some special buildings, and we built and construct some, how to say, box, yes, where you can come in, close the door, and all your phones are switching on, off, because it's a very reliable protection against any electromagnetic waves from the outside, yes. So if you build such kind of device, or you build some such kind of construction which totally shield all electromagnetic field around you, then you will have 100% protection against corona. Otherwise, if you left some small spaces where the electromagnetic waves can spread, yes, so this protection would be not 100% efficient.
Okay.
So, but it's cost a lot of money, so it's better to move your house away from the power line. It's easy. Okay, so thank you for. And now it's next presentation is mathematical modeling and control of hybrid source for application in electric vehicles.
That will be
Comes from Sofia, yes?
Yes, Bulgaria Technical University in Sofia. My name is Vladimir Dimitrov.
And your
Thank you.
stage is yours.
Thank you. I'm Vladimir Dimitrov. I'm from the Technical University in Sofia, Power Electronics Department, and I'll be talking about electric vehicles, how to model and control such a system. Our task was to build models for an electric vehicle and to compare different ways to construct such a vehicle. So basically what we have done was most people, when they think about electric vehicles, they think that they're powered from an electric battery, let's say lithium-ion battery. Here we have a table that compares the specific energy of hydrogen, lithium as the primary source, or the standard diesel and gasoline types of energy source. So when we talk about low emissions, the two primary ways to construct an electric vehicle, I think I'm talking about the electric source, is either battery, which is standard when you talk about electric vehicles, or hydrogen. The so-called fuel cell is the primary way to power a vehicle through hydrogen. And as you can see from this table, the hydrogen as an energy source has better parameters when we talk about energy density. So this means an electric vehicle that is powered from a fuel cell can be, let's say, specified for a longer range, and also hydrogen can be a lot faster to recharge. So we say, let's build an electric vehicle powered by a fuel cell. However, the primary problem with this approach is that the fuel cell, we have here a graph for a fuel cell, is not very efficient when we talk about high derivatives of the current. Meaning when we start accelerate or accelerate very fast or stop very fast, fuel cell is not very efficient. This is one of the primary problems with just the pure fuel cell as an energy source for electric vehicle. So our task was to build a model that hybridizes or combines some fuel cell with secondary energy storage, for example, a battery or supercapacitor, and compare this compare the ways to design such a system. So basically, our system is as follows. We have a vehicle model that we have developed in order to load the system, or our power conversion, the way to design the system. And as input sources, we have a fuel cell and a supercapacitor or lithium battery as secondary storage. The idea is to use the fuel cell for, let's say, energy related issues, meaning long range. And for the dynamics, use a supercapacitor as the energy source, which we accumulate and recharge and charge very fast if we want faster dynamics, for example, acceleration. This graph is for a powertrain system of so-called Honda fuel cell vehicle. It's a commercially available vehicle that uses hydrogen and fuel cell as the primary energy source. And the idea is to use the capacitor power, this secondary energy source, during startup, and the fuel cell acts as the primary energy source during long ranges. So what we have done is build a model for the vehicle that inputs a standard cycle that is used for testing the vehicle. For example, VLTC, these are standard cycles that postulate the vehicle speed over time, and use this model to test different ways to design the power conversion system and their control system. So, what are the ways to design such a system? First, the vehicle model. The idea is to have an input which is from the standard cycle that is used to test the vehicle. We have the following equations model the aerodynamic force and the rolling resistance as the primary sources that, let's say, resist the motion force from the, let's say, battery or the electric motor. And using this model in Simulink, modeled a standard vehicle. These are the equations for the whole system. The aerodynamic drag and the rolling resistors are standard forces. They are appropriate to the speed and the speed squared. And the primary model that we have done is for the electric motor. The electric motor usually is specified by its RPM versus torque equation. And we have done a system that regulates the speed that comes from the cycle and output the motor force in order to model the whole vehicle. The vehicle is used, this whole system is used to load our converter. So here we have a current source that is that its value is regulated according to the speed that the vehicle needs to obtain in any let's say in different point of time. So here we have a standard cycle. This is the VLTC cycle that sets the speed as a function of range in order to test the vehicle for emissions and fuel economy. And our model follows more or less accurately the standard cycle. So we use this model in order to design such a system. Basically, we have two approaches. The one is to use the fuel cell and charge a supercapacitor through a unidirectional DC-DC converter, and then the supercapacitor charges the motor or the, let's say, the electric motor in the vehicle through a bidirectional DC-DC converter. This is the so-called Kascak approach. And the second approach is so-called parallel approach, where the load or the electric motor, this is our model for the vehicle, is powered to the fuel cell and supercapacitor in a common DC bus. So the fuel cell and the supercapacitor, through the same converters more or less, power a common DC bus that powers the electric motor. So our task was to design models for these two ways to design a hybrid energy source for an electric vehicle, compare them, of course, and obtain results. So what we have done for the Kascak approach, this is our primary model in Simulink. We have the fuel cell. One of the parameters are given in the paper, but the overall idea is to have the same fuel cell and the same supercapacitor, and more or less the same DC-DC converter, the unidirectional and the bidirectional one, and just change the layout and compare efficiencies and ways to control the whole system. So this was the first approach. The unidirectional one, or the bidirectional one, that is between the supercapacitor and the electric vehicle, we have a standard half bridge system where the supercapacitor is connected here, the DC bus is connected here, and this converter can boost the voltage from the supercapacitor or buck the voltage from the electrical vehicle in order to apply, let's say, regenerative motion. When the vehicle stops, we regenerate the energy and charge the supercapacitor. For the unidirectional converter, we have a standard buck topology where the fuel cell is usually at a larger voltage than the supercapacitor. We need to buck this voltage in order to charge the supercapacitor if it needs charging, or shut the converter off when the supercapacitor is charged. These two converters are standard, and we have used them in both cases, in the Kascak approach and the parallel approach. The second topology, the same idea, but the two DC-DC converters are connected in parallel and charge the electric vehicle, the same converters. And for the control systems, for the unidirectional converter, it's powered by the fuel cell and needs to charge the supercapacitor. So our idea was to implement a constant current charge, where the fuel cell is discharged with constant current that allows for maximum efficiency of the fuel cell during its operation. And we have designed such a control system that we have a feed regulator. The loop is closed by the fuel cell current, providing constant, of course, charge from the fuel cell. And we have a block that controls if we need to consume energy from the fuel cell. We check if currently the electric vehicle is moving or the supercapacitor needs charge, and decide whatever to allow this system to work to load the fuel cell. So the fuel cell is loaded with constant current or no current at all, depending on the motion of the vehicle. So for the bidirectional converter, again, we have a converter that needs to be charged from the supercapacitor and must output constant voltage in order to supply the motor with constant voltage for its operation. So here we have a more complicated system. We need to more or less regulate the output voltage regardless of the topology used. This voltage is used to power the motor. So we have as feedback the motor voltage. Here we have the voltage from the motor, and the reference is given from the supercapacitor. Again, we have a comparison. If the voltage of the supercapacitor is too low or the supercapacitor is overcharged, we must shut down the system and consume only from the fuel cell. So we check if the supercapacitor is overcharged or undercharged, and we have implemented a standard current loop, internal loop, in order to obtain better dynamics. But the overall idea is to regulate the voltage at the output of the converter. So using these two models, the same control system, but different configuration for the unidirectional and the bidirectional state, we have implemented a standard VOTC cycle. This is the top graph, which sets the current that is needed from the vehicle in order to obtain the speed. And we have compared the fuel cell current that is constant in either charge. In either case, the supercapacitor voltage, is a main, let's say, parameter in this system, because its variation actually says a lot about the system. If we oversize the capacitor, we usually obtain a very narrow change of the supercapacitor voltage, but the supercapacitor is something that is very expensive in the system and adds weight to the overall system. So this is one of the equations that we need to take in mind when optimizing the system to allow for a reasonable derivation of the supercapacitor voltage. And of course, at the output, we have the load voltage that is powering the motor in the system. So for the Kascak topology, we have found that the overall efficiency of the conversion, because we have two conversions, one from the fuel cell to the supercapacitor and then from the supercapacitor to the motor, is lower. And this topology, if we optimize the overall efficiency of the system, is worse. However, the control effort, the two control systems are a lot easier to design and to obtain, because the regulation of the output voltage and the fuel cell current are not intermixed, and we can easily obtain independently constant current from the fuel cell and constant output voltage. And for the second case, we have the so-called common DC bus or parallel topology, where both converters are outputting their energy to the motor. Again, the first curve is the load current that our model of the vehicle needs in order to obtain this cycle. However, here we have the following observations. First, both converters are, let's say, intercommunicating in actually not very pleasant way, because one of the converters need to charge actually discharge, sorry, the fuel cell with constant current, and the other converter that is powered from the supercapacitor needs to set the output voltage at a constant value. So these are more or less conflicting, let's say, conflicting tasks for the two control systems. So we need to be a lot more careful about the design of the control system, and we had a lot of problems until we had this final, let's say, waveforms. But the system has a lot of better efficiency overall. So designing such a system that has a common DC bus is a lot better when we talk about range and efficiency, with the main problem being that the control system is, let's say, a little bit complicated to design. So more or less that was my presentation, and of course thank you for your attention.
Thank you for your presentation. It's quite interesting. So questions from the audience? Okay, my question is, you talk about efficiency, yes? And how you evaluate the efficiency of your system? Because efficiency is a general word, but what parameters you compare between two models? Just say this model is efficient than another, more efficient than another model.
So basically we have the switching losses and the conduction losses in the both converters that need to be combined, and the overall efficiency is the amount of energy that we require from the supercapacitor and the fuel cell in order to, let's say, run through the cycle. How much energy we need to consume from the fuel cell, and how much energy do we recharge and charge from the supercapacitor in order to, let's say, run a standard cycle. This is our idea for efficiency. If we consume minimum hydrogen from the fuel cell, and let's say the supercapacitor is recharged more or less with more variation on the supercapacitor voltage, because the supercapacitor voltage is connected to the energy of the supercapacitor, we have a overall more efficient system, because we consume less resources from our hybrid energy source to have a standard cycle.
Okay, so you save the life of the fuel cells by adding some supercapacitor, yes?
Yeah, it can be a battery also, but
yeah, it can be battery also. But okay, it's for the ideal situation. But if you have some, you talk about the electrical vehicles, yes?
Yeah.
And it's a dynamic system, yes? Mm-hmm. You driving faster, slower, and so on and so on. Your system help to extend the lifetime of the fuel cells. And it's much the needs of the dynamic system. Maybe your system are not so dynamic when you add some capacitor, yes? And
yeah,
the control algorithm are not allowed to be so dynamic to move very fast and then move very slow and so on and so on.
Yeah. If you have only a fuel cell, the dynamic acceleration is worse. This is one of the problems. The second problem is you do not have the possibility to have regeneration. For example, when you move downhill, you cannot generate hydrogen just because your electric motor is running as a generator. But when you have a supercapacitor or battery, let's say, you can also regenerate energy from the moving of the vehicle. This is another benefit when you have a secondary, let's say, energy source that is capable of regeneration. So supplying and sinking energy. This is the second idea, to have not only acceleration and better dynamics, but overall efficiency by able to regenerate some of the energy that is available in the system when you're moving downhill, for example, or let's say wanting to lower your speed.
Okay, so a very interesting presentation. I have a lot of questions. I can ask a little bit more questions, but now time is running out and we have just time for one presentation, for the last presentation. So thank you very much for your very interesting presentation. Maybe next time we will ask more questions about your interesting system. And now we have the last presentation, and it's come from Turkey, yes?
Yes.
And
yes.
The title of the presentation is Novel Single-Phase Modified Quasi-Z Source Inverter Circuit Design and Analysis. Oh, it's a very complicated title for power engineers. So your stage, and you can...
Yes. Hello, good afternoon, everyone. Do you hear me?
Yes.
Good. Thank you very much for joining my presentation. Today, I am going to talk about novel modified quasi-Z source inverter circuit. I am a PhD student. Actually, I'm a PhD candidate right now. And we have been working with this topology inverter for more than 2 years. Let's start with the content of my presentation. Okay. I will talk about, first of all, I will take a look, take a look at the inverter background. Then I will talk about the principle of the Z-source inverters and quasi-Z-source inverters. They are also called impedance source inverters. Then I will talk about Then I will talk about the additional switch boost and modified unipolar PWM technique that we have implemented in our circuit. This is actually the novelty part of our circuit. At the end of the presentation, I will show you the simulation results. Let's start with the definition. A power inverter is an electronic device, as we already know, that changes DC power into AC power, and that can be used for many devices. For example, home appliances, power tools, electric lights, AC motor, speed control units, UPS, and PV systems. The input source, DC voltage source, can be a 12-volt battery or several connected batteries, full cell stack, diode rectifier circuits, supercapacitor, or PV module. All can be a voltage source of our inverter. Conventional inverters can be classified as voltage source inverter and current source inverter. They operate either in buck or boost mode. The switches, the power switches in the inverter bridge of the same leg cannot be triggered at the same time. This could be very dangerous for the inverter general purpose. Therefore, that time should be located between the top and bottom switches of the same leg, and this causes output distortion. This is also a drawback. Furthermore, they have two-stage power conversion. Either we have to use AC trafo, transformer, or DC-DC converter to step up the boost the DC power if we do not have a required DC power to convert in the inverter bridge, and therefore they are open. They are open to the effect of electromagnetic interference. In the figure, we can see both the voltage source and current source inverters. To overcome the mentioned drawbacks, Z-source inverter topology was introduced by Peng in 2002. Z-source inverter has a unique impedance network consisting of 2 equal inductors and 2 equal capacitors, as can be seen on the figure below. And because of the impedance network, we don't need any DC-DC converter or a transformer. This impedance network is already able to buck and bust the inverter. According to modulation index, we can boost or we can buck. We can operate in buck or boost mode. So, in the recent years, quasi Z-source inverter topology has been introduced with a slight modification in the Z network, as can be seen in the figure below. This is also an improved topology of the Z-source inverter. It has all the advantages, but it has eliminated some of the drawbacks. Z-source inverter is not able to draw a continuous input current from DC power because it has not an inductor placed after the DC power source, and because of that, the quasi Z-source inverter is able to draw a continuous input power, and it has a lower component ratings in the impedance network, especially the 2 capacitors the values of the 2 capacitors can be reduced because of the quasi Z-source inverter characteristic. To summarize the principles of Z-source and quasi Z-source inverter, normally single-phase inverters or 3-phase inverters have either 4 or 8 vector states, active states and 0 states. Together with these states, Z-source inverters have an additional state defined as shoot-through state, during which the switches are short-circuited, which is not allowed by the voltage source or current source inverters. So we can short-circuit the switches in the same phase leg, in the 2 same phase leg or in the 3 phase leg. This will not be a problem in this circuit topology. In shoot-through state, DC energy comes into the Z network from the DC power source, and this stored energy, the energy is stored in the coils, and after in the non-shoot-through state, the stored energy and plus the DC power energy is transferred into the load inverter bridge. So the step-up process, namely the boosting operation, is provided. Related to our study, there are 2 main questions. We have asked to us, how can we increase the boost factor, the gain of the circuit, and how can we reduce the harmonic content? How can we reduce the total harmonic distortion in the voltage and current at the output? This paper proposes a novel single-phase modified Z-source inverter, which has a high boost voltage conversion ability and reduced THD value. So move on the next page. So we can say, maximize the boost efficiency and voltage gain. We have placed an additional boost switch, S5, between the impedance network and inverter bridge. So this additional bridge behaves like a boosting process, and it operates only in shoot-through states. In normal mode, in active states, this switch is not triggered, and in operating, it operates only in the switch in shoot-through state. So we can see we have 2 operational modes in the impedance source inverter, in quasi source inverter topology. In the left, we can see non-shoot-through state, and the right, we can see the shoot-through state. The additional switch that we place before the inverter bridge is operated only in shoot-through state. We have used an AND gates. We have sent the AND gates to the gate pass of the switch. But when the inverter switches are operated in non-shoot-through state, the additional switch is not used. So we can say this additional switch is used only a small time interval. So secondly, for the second question, total harmonic distortion for the voltage and current at the output is reduced because of a modified unipolar PWM technique adapted for the proposed circuit. So we can see in the figure the normal unipolar PWM operation principle. Normally we have two modified reference modulated waves and one carrier waves, triangular waves, to generate the required pulses for the switches. But in our study, in the unipolar PWM study, we have applied it differently from the usual way. The diagonal switches are driven at the same time. In the previous page back, we can see the first switching signal is generated here, and the second signal is inverted using NOT gates, is generated here. But in our study, we don't have any AND gate signal, AND gates. So we are using as diagonal. The first generated pulse signal is sent to the S1 signal and S4 signal. So the second generated pulse signal is sent S2 and S4, S3 signal. So we can see in the right picture, the pulses, the generated pulses for the S1 and the generated pulses for the S3. These are the switches of the same phase leg. So when we look here, in this time, they are both switches, upper switch and lower switches are short-circuited, and these are the shoot-through pulses. So with these shoot-through pulses, these, when we concentrate at the shoot-through pulses, these are not constant. These varies every P/3 cycle. So when we look at the shoot-through periods, we can use to calculate the duty cycle, we can use this formulate. In a cycle, the shoot-through duty ratio varies periodically, each P/3 in a cycle. So it can be controlled by modifying the control waveforms. When we increase or decrease the modified waves, we can change the period, but the D is constant. So when we calculate the duty ratio, we come to this constant formula. So using this boost factor, this formula, we can get the boost factor, and using modulation index and boost factor, we can calculate the gain of the overall circuit. So I'm coming to the simulation results. All the simulations were performed using MATLAB Simulink, and we have selected parameters according to our circuit switching frequencies, input source, etc. So we have took capacitors 160 microfarad, 470 microfarad, and inductors are 160 microhenry. The switching frequency is 2.5 kilohertz, and the inductance and capacitance values of the output filter are 1 millihenry and 100 microfarad. And we have load resistive and inductive load. So this is the general main circuit configuration. These are the subsystem to generate the required pulses. These are the DC power source. These circuit part is the impedance network. There are two inductors, equally same inductors, and two capacitors to boost the voltage. After this, we have put a additional switching boost. These two generating pulses have been connected using AND gates, and the output of the AND gate has been triggered to additional pulse, so to increase the DC bus voltage. Coming to next page. The first aim of the simulation is to show the boosting effect and compare the results of the circuit. We have selected two modulation index and two input voltages. First of all, the 0.6 and 20 volts, and in the second scenario, the 0.8 and 50 volts respectively has been selected. And with and without using additional switching boost, we have run the simulation. So when we look at this graph, this shows us without switching boost, we have reached about 62 volt peak value of the output voltage. But when we use the additional boost switch, the output voltage has been increased to 91 voltage. For this is for 0.6 modulation X. When we have 50 volt input voltage and 0.8 modulation index, we have increased the 155 volt into 200 volt by using additional boost effect. So it is very clear the output voltage has been increased by using this additional boosting switch. The second aim of the simulation is to show the THD reduction because of a unipolar PWM effect. We have very good THD at the output. THD simulations are also performed using MATLAB Simulink fast Fourier tool, analyzing tool. And coming to the figures, so there are also many pass-width modulation control techniques according to related to Z-source inverters. These are simple boost, maximum boost, and maximum constant boost control techniques. And this is the output result of the simple boost. This is output result of the maximum, and this is output result of the maximum constant boost THD result. But in our case, we have a very good THD result under the same circuit conditions. So coming to conclusion, for each modulation technique, the same filter circuit has been used with the equal inductors and capacitors. Using modified unipolar PWM technique, we have acquired 2.33 THD, which is very under the IEEE standard harmonic limits. It's very clear to modified that modified unipolar PWM has a great impact on the THD reduction for the voltage and at the output compared to the traditional modulation technique. So the proposed circuit is very effective for achieving higher boost on output voltage and current by adding a simple boost switch. The only drawback could be that we have placed an additional boost and we have used an additional boost, but this additional boost operates only in a small interval time, and the switching loss could be very, very small, and therefore it can be eliminated, but the output voltage has been increased, and therefore it is very useful to apply this additional switch. In addition to this, unipolar PWM technique is also utilized in a different way from the traditional implementation to generate shoot-through passes and to reduce voltage and current distortions. That's all I have to say about my presentation.
Okay, thank you very much for your extended presentation. And please question just 1 or 2 questions because we don't have time. So, attendants, please questions. Okay, so from, Darius and Zhukaitis.
No questions from my side.
Okay, just 1 question. You show the results which you get on Simulink, yes?
Yes.
Yes. Do you planning to test on real implementation of your?
Yes, I have been working on the experimental setup right now.
Okay, so it will be very interesting to see your results.
Yes.
And how they match with the Simulink result.
And we can compare the simulation results and experimental results to get better accuracy.
Okay. So thank you very much for the attendance. It's the end of our session. I hope it will be interesting for you to listen presentations of your colleagues, and goodbye. Have a nice evening, and see you next time.
Thank you.
Bye.
Thank you.
Bye.
Bye.
Bye-bye.